So if we come back to our situation with this rock that we found, we can figure out what the substance is if we can figure out, how much energy it takes to increase its temperature, and how much thermal energy, can be transferred to and out of it. And so we use the technique called calorimetry to do this. What we do is we heat up our substance typically, and in this case, we'll heat up this mass, this rock, place it into neutral water or room temperature water, mix it around, and then the water temperature is going to increase and this temperature will decrease. And if we know, the initial temperature of this, we know the initial temperature of this, we know how much mass this has, we know how much mass this has, we know the specific heat of water, and therefore the only unknown is going to be the specific heat of this mass. And so what we're going to be dealing with here is once we place that mass inside the cup, once we take that mass, we place it inside the cup, we cover it up, we're going to have a closed system because no mass after that point is going to enter or leave as best we can, and then energy is going to be exchanged between the water and the mass, and then based on that we can figure out what happens and what kind of substance this is. And so a calorimetry, we do this, this technique. We have to be very careful to transfer it very quickly, and this technique is important, to get this right, to be able to figure out what kind of substance you have. So this principle is where we have energy out of one part is going to equal energy into the other. And so, to say this kind of very basically, the energy or heat lost by one, right, is transfer one is going to be gained by the other. So this mass is going to cool down. It's going to transfer its energy into that water, and then that water is going to heat up. So the sum of all the heat lost and the heat gained should equal 0. So if we add up all the Q's, all the thermal energy loss, thermal energy gain, that'll all add up to be 0, and we're going to use that as we continue here. So let's take a look at this example. Let's say that we have a mass, we'll just call this rock R, 100 grams, with the initial temperature is 75 degrees Celsius, which we'll need in kilograms, which you got here. And let's say we have a calorimeter cup filled with water, 0.5 kilograms of water. The initial temperature of that water is 10 degrees Celsius. And then after we place it in there, the final temperature of them will be 10.398. And so what we want to find out is what is the specific heat capacity of the rock? And so if we set up our sum of the Q's to equal 0, we've got that. And what we're going to do is we're going to take a look at both Q of the water, Q of our unknown substance, X. And when we set this up, we know, we have the mass of the water, specific heat of the water, temperature final minus temperature initial of the water. Then we have mx, so for this rock here, times the specific heat of the rock, T final minus T initial of the rock. And so when we place all our values in there, and make sure that you do this properly here, and be careful with your algebra, you're going to get the final specific heat capacity. So go ahead and solve this, and then when you're ready to check your answer, you can check that here. Okay, so you should get 128.95 joules per kilogram degrees Celsius as this substance, and so very close to one of those ones in the table there. So if we look at that, it's very close to lead, so it's probably lead with a little bit of error in there. And so that's what essentially you should be able to do with a calorimetry lab is take the substances, get those temperatures, get those masses, and figure out what you have. And so this is a listing of the masses that we use in our room. You're either going to have one of these masses or one of the ones underlined, either aluminum, copper, iron, or lead, or bronze, brass, stainless steel. And so one of your masses will be that. And so the one that's your closest to is most likely that, unless you had considerable error. Let's go ahead and take a look at this here with L5. We've got a bolt, 0.050 kilogram bolt with an initial temperature that we want to find out, and we know the final temperature is 25 degrees Celsius. The specific heat capacity of it is 899. And we have the water here, which is 0.15 kilograms. The initial temperature is 21 degrees. The final temperature is going to be the same, right, for both of these after you place it in there. This is the specific heat of water. And so we're going to place it in there, and we can figure out what the initial temperature of the bolt is, and that's what we're going to find out here. So go ahead and pause the clip and set up all some of the cues here with all the variables. Be very careful with your algebra there and see if you can figure out what the initial temperature is. And so go ahead and pause the clip and give it your best shot, and then when you're ready to check, you can hit play to continue. All right, so we have the mass itself, and then we have the calorimeter cup of water. We can place our values in there. This is our unknown, right? So this is what we need. If we're careful with the algebra there, we'll multiply these in to here. We'll multiply these into here. We can multiply these into this, and then we can multiply those two into this, where we end up getting 44.95 times Ti. That's our only unknown. And when we solve for Ti, the initial temperature of that bolt should be 80.875. So it started at 80.875, and then the final temperature is 25 because it cooled down inside here. And then the water heated up from 21 to 25. And so because we know how much the water heated up, and we know, everything else here, we can figure out that initial temperature. All right, so 2 kilograms of water, 15 degrees Celsius is mixed with 4.77 kilograms of water. At 75 degrees Celsius, what's the final temperature of the water? So in this case, as we draw these out, we have one that's warmer than the other, the 75 degrees Celsius water. And it turns out you actually use the exact same method because the thermal energy gained by one should equal the thermal energy lost by the other. And so when we set up this, again, some of the cues, but in this case we have water and water, right? And so if we split this up into, water 1, water 2, we can find that energy transfer. And so go ahead and pick one for one side, one for the other, and figure out what the final temperature would be. In this case, you have to be careful again with your, your variables here. With this is our unknown right here, T final. And so you're gonna have to be careful with your algebra here to figure that out. So go ahead and pause the clip and give it a shot here, and then when you're ready to check, you can hit play to continue. All right, so we've got our values, multiply those in, and so the big thing here is factoring this, right? We multiply this, this becomes 8372. We'll multiply that into here, then we multiply that into 15, and then we take these two and then multiply it into T final and that into here. So then T finals, and then when our basic numbers are set up there, and so our T final should come out to be 57.273 degrees Celsius. So that's the equilibrium temperature of those two. So in this one, let's say that we actually have a cup that's going to, can influence this here. So we have, our mass of lead here, 0.45 kilograms, starts out at 95 degrees Celsius. We have an aluminum cup. Now this aluminum calorimeter cup will be able to heat up. Up until this point, we've used insulated containers. This one can actually heat up. So the initial temperature of this calorimeter cup is 15 degrees. And then the water inside is 0.4 kilograms. The initial temperature is 15 degrees Celsius. And the water itself is 4,186 joules per kilogram degrees Celsius. So what we want to find out is what is the final temperature of all three. So in this case, and here's some values here. The aluminum is 900 joules per kilogram degrees Celsius. And we've got lead up there as well. So we're going to actually set up all three. We have the sum of the Q's of all three. So, Q of the water plus Q of the aluminum